Let's look at OpenStack's College Physics, Chapter 15, Problem 55. A large electrical power station generates 1,000 megawatts of electricity with an efficiency of 35%. Calculate the heat transfer to the power station, QH, in 1 day. B. How much heat transfer, QC, occurs to the environment in 1 day? C. If the heat transfer in the cooling towers is from 35 degrees Celsius, water, into the local air mass, which increases in temperature from 18 degrees Celsius to 20 degrees Celsius, what is the total increase in entropy due to this heat transfer? D. How much energy becomes unavailable to do work because of this increase in entropy, assuming an 18 degrees Celsius lowest temperature? Part of QC could be utilized to operate heat engines for simply heating the surroundings, but it rarely is. Let's start writing out our knowns and unknowns. So we're told that the power station generates 1,000 megawatts of electricity. So some energy is put into this power station so that the power station generates that much electricity. So that's going to be, since it's in watts, that means that it's a power, but that's the power that's done by the work output. So I'm going to call this P is 1,000 megawatts, and the efficiency is 35%. In part A, we want to calculate the heat transfer to the power station in 1 day. So we want Q sub H in 1 day. In part B, we want QC also in 1 day. In part D, if the heat transfer is then in the cooling towers is from 35 degrees Celsius, so we know temperature in the cooling towers is 35 degrees Celsius, and that is going into a temperature of 18 degrees that then raises the temperature to 20 degrees Celsius. We're looking for the increase in entropy, so we want delta S. And in part D, we want to know how much work is unavailable, so W unavailable. All right, so the diagram is basically the diagram of a heat engine. So this is the power station. It gets energy, so this would be the QH. It does work and it sends some heat into the environment. So as I said before, this power is work divided by time. So I know that power is work over time, which means that work is power times time. But I'm not looking for the work. I want the QH. So I know that the efficiency is work divided by QH. So that means that QH will be work divided by efficiency. Well, work is power times time divided by efficiency. So the power is 1,000 megawatts, so that's 10 to the 6th watts. Time is 24 hours, but there are 3,600 seconds in an hour. And we divide this by the efficiency, which is 0.350. So once we plug these numbers into our calculators, we end up with an efficiency of, with a heat of 2.47 times 10 to the 14th joules. All right. So this was part A. In part B, we're looking for QC, and we know that by conservation of energy, QH has to be equal to W plus QC. So then QC is QH minus W. And that's 2.47 times 10 to the 14th minus W, which is just power times time. So that is 1,000 times 10 to the 6th times 24 hours times 3,600 seconds. And when we do the math, we end up with 1.6 times 10 to the 14th joules. So this is our QC, and this was our QH. Now, in part C, we're looking for the change in entropy. So that is the entropy lost by the hot reservoir plus entropy gained by the cold reservoir. So really, our hot reservoir here is not the QH we solved for before. We're just looking at the heat that came out of this engine that came at 35 degrees Celsius, and it changed the air around it from 18 degrees Celsius to 20 degrees Celsius. So the Q hot that we're using here is actually Q cold, because we're just looking at there's a new process that's happening here. This heat coming from the engine is going to heat up the air. So then we write delta S as entropy lost is negative, so that's negative the QC we had there divided by 35 plus 273. We have to convert from Celsius into Kelvin plus QC divided by, so we have to average out the 18 degrees and the 20 degrees. So that would be 18 plus 20 divided by 2. And to that we add 273. So that will be, what's QC? 1.6 times 10 to the 14th. I'm factoring it out. 1 over 308 plus 1 over 292. And when we do the math, we end up with 2.85 times 10 to the 10th joules per kilogram. Joules per Kelvin. All right. In part D, we're looking for the work unavailable. So work unavailable is the entropy change that we just solved for times the lowest temperature that we have in this particular problem. So that will be 2.85 times 10 to the 10th joules per Kelvin. And the lowest temperature is the 18 degrees. So that's 18 degrees Celsius plus 273. And when we multiply these numbers, we end up with 8.29 times 10 to the 12th joules. So this is how much unavailable work there is.